As we have seen, these raising and lowering operators have allowed us to write the Hamiltonian operator in a particularly elegant form, and to define a number operator. The real elegance of these operators comes, however, from what they can do and the physical insight they can provide. Unlike most of the operators we have dealt with so far, these ones are unusual. They are not, for example, Hermitian operators, and they do not correspond to physically measurable quantities. They are, however, particularly useful when we want to describe physical processes. They allow us to greatly simplify the algebra of handling particles, and they themselves have a particularly simple but powerful algebra. That algebra is based around one particular relation, specifically the commutation relation between the raising and lowering operators.
The operators A and A dagger have a very important property, which is their commutator. That is, specifically, we would find that if we take the commutator of A and A dagger, which of course is A dagger and minus A dagger A, that would equal 1. This is quite straightforward to prove, and we'll leave it as an exercise. This relation is so useful that it's worthwhile memorizing. If we use the word less in its meaning as minus, we obtain quite a rhythmic phrase here. Specifically, A dagger less A dagger A equals 1.
As I said, this relation is really the only one you need to learn to use these raising and lowering, or creation and annihilation operators. It's the main relation we use in algebraic manipulations, and most of the other properties of these operators can be derived from it. So, I apologize if it seems like I'm taking you back to the earliest days of your education when you were a small child in your first classes, and I'm sure you were not expecting this in a quantum mechanics class. But I'm going to ask you to repeat it with me a few times. This really is the easiest way to learn it. So, A dagger less A dagger A equals 1. Try it again, say it along with me. A dagger less A dagger A equals 1. And finally, one more time. A dagger less A dagger A equals 1. Thank you for your indulgence here. I promise you it's worth this childish little exercise.
We can use this commutator property, which we've written out here, A dagger less A dagger A equals 1, together with our number operator property, A dagger A operating on psi n gives us n times psi n, to show the reason why these operators are called raising and lowering operators, or creation and annihilation operators. If we operate on both sides of this number operator expression with A, the annihilation or lowering operator, we have obviously A operating on A dagger A operating on psi n is equal to n times A operating on psi n. We can regroup on the left, simply moving the parentheses here, so we've got A dagger operating on A psi n is equal to n times A psi n. Now we can substitute for this expression here from the commutator. Explicitly, here's our commutator, and so therefore substituting using this commutator, which gives us A dagger is equal to 1 plus A dagger A. Substituting on the left, therefore, this is what we obtain, and this is our right-hand side as before. And that means that A dagger A operating on A operating on psi n, that's this part here, is equal to n minus 1, we've taken the 1 over there, times A operating on psi n. But this expression we've just worked out means that, from our number operator expression, A operating on psi n is simply psi n minus 1, at least within some normalizing constant, an. Simply from our number operator expression, A dagger A operating on some state, giving us n minus 1 times the same state, means that state is state n minus 1. Hence, A operating on psi n gives us some constant, an, times psi n minus 1. And we see why this operator, A, is called the lowering operator. It changes the state psi n into the state psi n minus 1. We can perform a similar analysis operating on both sides of the same expression with A dagger, and the details of this are left as an exercise. The net result is that we would get A dagger A operating on A dagger times psi n is equal to n plus 1 times A dagger psi n. So therefore, similarly, using our number operator relation, we conclude that A dagger psi n is simply psi n plus 1, at least within some normalizing constant, which we'll call Bn plus 1. Hence, A dagger psi n is equal to some constant, Bn plus 1, times psi n plus 1. And we can see why the operator A dagger is called the raising operator, because it changes the state psi n into the state psi n plus 1. Incidentally, one way to remember which operator is which in these two expressions here is to think of the superscript dagger as being like a plus sign, corresponding to raising the state. So this operator, the A dagger, is the one that raises the state, takes psi n to psi n plus 1. Indeed, it's also a common notation to use a superscript plus sign instead of the dagger. Now we can work out these normalization coefficients, an and bn. We can pre-multiply an psi n, which we already know is this normalizing coefficient an times psi n minus 1. We can pre-multiply that by psi n minus 1. And, of course, that just gives us this expression here, but because a psi n is equal to this an psi n minus 1, then pre-multiplying by psi n minus 1 just gives us an. Now, psi n minus 1a is just the Hermitian adjoint of A dagger psi n minus 1. Remember, when we take a Hermitian adjoint, we take the flipped round product of the Hermitian adjoints. And we can rewrite this expression here as Bn psi n Hermitian adjoint, because A dagger psi n minus 1 is Bn psi n. That is, we know that A dagger psi n was Bn plus 1 psi n plus 1. So therefore, A dagger psi n minus 1 is just Bn psi n. So therefore, we know that psi n minus 1a is just Bn psi n dagger. So, using this, we can, of course, take the Hermitian adjoint explicitly. That gives us Bn star times psi n as a bra vector. So, therefore, if we write psi n minus 1a psi n, that just means post-multiplying by psi n on the right here, that simply gives us Bn star. But we already know that this expression here is also an. A operating on psi n gives us an psi n minus 1. So this left-hand side here is an, but also we know it's Bn star. Hence, A dagger A operating on psi n, which of course is just an A dagger operating on psi n minus 1. Well, this, of course, is Bn psi n, so this whole expression here is an Bn psi n. But Bn is an star from this relation here. So this is mod squared of an. So A dagger A operating on psi n gives us mod squared an times psi n. But we know from the number operator relation that this is just n times psi n. So therefore, the modulus squared of an is just n, the state number. And so an is therefore the square root of little n within a unit complex constant, and we make the choice that that unit complex constant is +1. Because an is now just this real number, the square root of n, then so also bn must be that same real number, so bn is root n also. So instead of a operating on psi n being an psi n minus 1, we now explicitly have that a operating on psi n is root n times psi n minus 1. And similarly, instead of a dagger psi n just being bn plus 1 psi n plus 1, we now have explicitly that a dagger psi n is equal to the square root of n plus 1 times psi n plus 1. And these are two very important relations for working with creation and annihilation operators. Now, we know that the harmonic oscillator has a lowest state, and that corresponds to n equals 0. Hence, from this relation that we've just derived, we must therefore have that the annihilation operator operating on that lowest state simply gives us 0 because the square root of 0 is 0. This gives us an alternative way of actually deducing what the lowest energy eigenstate actually is, and we could write it again back in its form psi naught of xi. Using our differential operator definition of the annihilation operator, we therefore have that the annihilation operator operating on the lowest state gives us 0. Well, this gives us a simple first-order differential equation for working out the lowest state, psi 0 of xi. And we can easily check, therefore, that the solution is in this form. We've also normalized this form, which is where this 1 over the 4th root of pi comes from. But it's easy to check that this is a solution of that first-order differential equation. Now, more importantly, perhaps, we can construct all the solutions for different n by successive application of the creation operator to that lowest state. Operating n times with the creation operator on the lowest state, psi 0, gives us the square root of n factorial times psi n. So this is a way of representing psi n. And so to make it normalized, we could write psi n, therefore, is 1 over the square root of n factorial times the creation operator to the nth power operating on the lowest state. In this kind of a way, each eigenfunction can be deduced from the preceding ones progressively, and we can use this expression in particular as a substitution to allow convenient manipulations of the states by operators.
Why then have we introduced these raising and lowering operators? Well, first of all, raising and lowering operators give us a compact and elegant way of stating the properties of the harmonic oscillator, a way in which the properties can largely be stated without using the actual wave function in space. This more abstract approach is particularly useful as we generalize the harmonic oscillator to other results where the oscillation may not really be describing the position of some mass, and hence where the concept of a wave function in space is possibly not meaningful. A good example of such a situation is the electromagnetic field, and we will turn to this next. Note, incidentally, that saying that the harmonic oscillator is in a state n is mathematically identical to considering that the harmonic oscillator mode contains a number n of identical particles, where each such particle has an energy h bar omega, or h nu. It is, of course, meaningless to say what order the particles are in. We can only say that we have n identical particles in the oscillator mode. This is exactly the kind of behavior we expected for identical bosons.